matrices. I'll do some review of matrices and so forth on Thursday. Okay, finding roots. I wanted to go through this in kind of a generalization as far as solving some equations. There's some pretty interesting tricks that you should be aware of. Now, you can find these in the book if you go through it, and also, of course, on the lecture notes. If I have two equations, and what I can do is solve for these terms right here, all right? These are the initial values. I can rewrite these equations. Very simple. Now, you know what these little subscripts mean when I have x and y on there? It means the derivative, all right? In mathematical terms, they tend to do that as a shortcut. So it means the derivative of f with respect to x or the derivative with respect to y, so forth, all right? I can rewrite this in this form, all right, so that if I'm looking for the difference x to x0, this delta x that we refer to, I can set it up like this as far as systems of equations, all right? So basically what I'm doing is just rewriting this into this form so that I can then solve for that delta x, all right? Now take a look at it for a moment, because if you haven't seen this before, you go, I wonder what's really going on. This thing down here, right, that's called the Jacobian. J-A-C-O-B-I-A-N, the Jacobian. Now you might want to remember that, circle that, because that Jacobian is constantly going to come up in a lot of engineering disciplines. And it's going to say, referring to the Jacobian or whatever. What it means is that you're solving that 2 by 2 matrix right there. All right, and these are derivatives with respect to x and y. Okay, now likewise, I can do the same thing for delta y, sitting down here. Notice, there's the Jacobian again, right? Sitting right there. How do you solve that? Remember how to do minors in matrices? We'll actually get into this later. But if I wanted to solve this, right, it's just that term, that product minus that product, that gives me the value, the Jacobian. Okay? Yeah, same as a determinant in 2D, or as a 2 by 2 matrix. Okay. So what I'm really after is the x plus 1. All right, so the x plus 1, the new value, is equal to the old value, or the previous value, minus that term. See, there's the Jacobian. All right, so let's say I want to find the root of this equation. All right, so here's an example. So I've got these two equations for f and g. All right, so I just plug these values into these expressions. All right, so here's f times gy minus gf of y, all right, and so forth. So here are the two expressions. Now, I'm going to start with some initial estimate, or some initial value. So I'll assume 0.1, and I'll use 0.5 for y. All right? Now, I run this 2 iterations, so I'm doing this thing in kind of a loop, right? Remember, so I'm going to check, run it, check for error. Okay, I got to do it again. Here's another simulation. So after 2 iterations, this is what I get. The exact answer, obviously x is 0 and y is 1. What do you think? Pretty darn good, right? And that only took 2 steps to do that. So when you're solving a set of equations, right, this is the way you want to go about doing that. What would you do if you had 3 equations?
You just put it in the 3 by 3 matrix.
Yeah. You wind up now doing a 3 by 3 matrix. How many 2 by 2s are in a 3 by 3?
2. 4.
Keep going. All right. Every combination 2 by 2 in there, right? So remember, you've got a series of operations you have to do. So just adding 1 row and 1 column to a matrix really amplifies the amount of work that you have to do. All right, error analysis. Okay, there are a number of ways to assess error. If ever you get into advanced courses like finite elements or advanced numerical methods or some of the things that you might do in some of the senior level classes or even graduate level, you will find there are a number of ways to calculate error. you have to look at two things, the accuracy and the precision. All right? Accuracy, how close you come to the exact value. That's exactly what we mean, just as a beat. That's known as validation. All right? Now, you're going to hear two words, probably later in your careers, of validation and verification. All right? Validation, verification. Validation implies how accurate you are in modeling the true mathematical expression of what you're trying to solve. You know, is this really the governing equation? In the verification, you're going to say, well, now that I've got the equation, how well does it actually fit with true, real-life, real-world experiments or values, you know, in the real world? Okay, the approximation. Does the approximation actually duplicate the true mathematical expression to be solved? All right, that's validation. Okay, so verification, validation, precision. How close you come to the truly measured values. That's what we mean. So remember those two words. They have a tendency to come up on quizzes. What's the difference between validation and verification? All right. For those of you that are marksmen, here's an example. Here, obviously, if you have a target, you're fairly inaccurate and imprecise. By the way, if you were shooting, what would this imply?
Jerking the
Trigger
trigger.
work on your zero.
Yeah, either I'm jerking the trigger or I've got some drift or something like that. By the way, last week I had never fired a 45 Magnum. Anybody ever seen a 45 Magnum?
I used a 44.
You know how big a 45 Magnum is? Did you fire one?
44.
Yeah, 44 is pretty big. This is a 45. That shell looks like a cannon. And I bet you know, there was a rock from here to the wall. And I didn't even come close. So that's what can happen, right? If ever any of you do any pistol shooting or any targeting. Okay, now what I want to do is increase the accuracy. So here, I've increased the maybe I've accounted for drift or whatever it is in wind, right? So I'm kind of centered around the target, but I'm imprecise, right? So in this one, you can see, oh, I'm clustered around here. Now, basically, what does this mean? What would you do on your rifle?
You're precise but not accurate.
Yeah, so
Adjust
you're
your
going
windage, zero
to
range.
adjust your windage a little bit and so forth. I remember being in the Army when we used to have to try to pick off targets at 500 yards. You know, 500 yards, man, you can't even see that far. So, you know, a lot of times you'd be lucky. So anyway, we spent a lot of time on the rifle range, you know, just tuning your rifle so that you could get it, you know, accurate. So anyway, you're clustering here, so you say, well, I've got to do some minor adjustment or whatever. So obviously what you're after is this. So that's what we mean by accurate and precise. Right? A good clustering around the center. All right, now, examples of error. Okay, there's truncation error. Remember we talked about this before. So if I have a series, and this series just keeps going on and on and on. Remember what that L means? In the font on this thing, it means dot, dot, dot. It just goes on forever. So,
Okay.
all right, so what we've got is, oh, this just goes on to infinity if I wanted. All right, that's the error due to the truncation. All right, that's what you're after, okay? If I want round off, now this is, for those of you that are into the accuracy of your computers, right, just how accurate are they? If this is plus and minus dot, D1, D2, so these would be digits, all right? That's supposed to be a dot, dot, dot. Then DP, BE, all right? So here's the definition. Number of significant digits with a base 2, base 10, base 16, whatever, and then the exponent, all right? Now, I'll show you what happens with this. Many years ago, we used to have to deal in hex when we were doing debugging of programs. How many of you remember hex? All right? Yeah, you want to tell them what it was?
That was the one that used letters, wasn't it? Like
Yeah.
A through F, so you went 0 through 15 for your,
Yeah.
rulers.
So you'd have to count letters up to a base of 16, and then you would have to find the error in the code and then work in hex. And talk about a nuisance. It was really bad news, but those were the days that was the only thing you could do. Okay, examples of error. Here's what we mean. In a 32-bit format, so you have 1 bit, that accounts for the sign, the plus or minus. You have 8 bits, that's dealing with the exponent, all right? 23 bits, whatever the significant digits would be, right? Here, P is 23, all right? How many PCs are 32-bit? Almost all. The new ones are 64, right? So now we go to 64, all right? Again, 1 bit, right? What's our base? Everything's always in 2. Why is it in 2 in computers?
Binary.
Yeah, exactly. It's either on or it's off. That's all there is to it. It's in the combination of those ons and offs that you have to get clever and do your programming. Now, instead of 8 bits, you're running 11 bits. All right, now look at the size of the exponent that you have here. And then significant digits, here you're running 52 bits. Quite a bit, quite a difference. The new AMD chips are running 64, right? Pentiums, Intel will be doing that as well. Now, examples of error. There are 2 kinds of errors. Circle this. This is important. This will show up again, probably on exams, and it will be carried through to the very end, because you'll have to be dealing always with estimations of error. 2 kinds of error that we'll deal with: absolute and relative. Absolute. Absolute value, the difference between the true value and the approximation, or the difference between the new calculation and the previous calculation. The absolute value of that is known as absolute error. All right? I use phi as some generic kind of variable. If I look at relative error, you notice what we're doing here? We're dividing, so it's the approximate value minus the true value divided by the approximate value. All right? So what we've done here is divide by the newest value, or the true value, if we wanted to do that. Okay? So this makes it relative. All right? So if I'm dealing with 2 very small numbers in here, you see what can happen? You can run 1 step and you say, oh, this thing's done. Right? It's converged. And you go, no, that can't be right. And maybe it's because I'm dealing with such small numbers, but I have to put it in perspective to the problem of what I'm trying to do. So that's why you do things as a relative error. So you're bounding the error between 0 and 1. You're not letting the round off of the computer kill the program or kill your iteration. All right? Relative error can be better than absolute error because that's the thing right there. It's scale independent. Okay, examples of error. Here's a propagation error. All right, so this means an approximation. Anytime you see an asterisk on something, it means it's approximated. That's usually the rule of thumb. Not always, but usually. All right, so here's an example. Here's a function, 2x cubed plus 3x squared plus 2x plus 1. All right, let's start out with a value 1.000001. All right, epsilon 1 times 10 to the minus 6. Right, so we got 1, 2, 3, 4, 5, 6. All right, so let's take the derivative.
I'm sorry, sir, is epsilon supposed to be your significant digits?
Yeah, so we're out here at the significant digit 1, all right? So look, here's the derivative, all right? So now I'm going to calculate here. I've got 14 times 10 to the minus 6. The larger the derivative, the approximation, the greater the error. You see what I'm saying? So you're going, now what does this look like? Where's this?
Taylor series.
Taylor series, right? Told you it's going to come back. It's always going to keep coming back throughout this whole course, this business of Taylor series. All right, so we're letting that epsilon be the difference, the error, right? Okay, so the rate of growth of error, something you must keep account of. All right, so here's an example of the rate of the error equal to some constant times epsilon. Rate of growth, C is a constant, it's a linear value. Here, it would be exponential, right? I just use K as a different constant to the nth power. So you can have a linear growth or you can have an exponential growth. All right, linear growth, that's normal. That's something you probably cannot avoid. It's just going to happen. It's going to have a continual round off that's going to be occurring within your computer, regardless of whether you're running the supercomputer or whether you're running this thing on your PC. Right? Exponential growth, that's what you got to watch out for. That's unstable. and you can get in big trouble. And usually you don't go too many steps before all of a sudden the solution is swamped or it's blown up or whatever. And so the system comes to a halt or it crashes because you've exceeded the numbers that it can deal with, whether you're 32-bit or 64-bit. All right, let's take a look at this example. Here's a simple series. All right, now remember the L dot dot dot. So here's some series that I have out here. E to the x minus whatever this expansion is, times n factorial. All right, so I can rewrite this so it looks like this. So n is equal to 0, 1, so forth, all the way out to something like that. Now, here's what happens. So if I start this out and I calculate that function, first step 1.71. Here's after the first step, after the second step, after the third step, right? It looks like it's coming down. Hey, now this time it picked up the 3 dots. How about that? All right, so here it is at the 8th. Uh-oh, what have we noticed here?
Increase.
Oh, yeah. Now, in just one step, it's jumped quite a bit. Now we go from here to here. What's going on? That's an example of what we mean by an unstable solution. And so here's what you should get as the exact answer, right? 0.15991. That's not even close. So what that tells me is that, I got a serious problem. I might as well stop because these programs aren't going to fix themselves. You're going to have to go in there and track it down and figure out what's going on. Okay, let's go back once again to Taylor series. All right, so here is the Taylor series. Right now, this would be in a more classical form where this is a what? Forward or backward series? Hint, look at the signs.
Forward.
Forward, right? Okay, so f of x, what would it be? It's f of a, whatever the value would be at x equal to a. First derivative, second derivative, third derivative, and so forth, all the way out, plus remainder. That's actually what the remainder looks like, if you wanted to do that, all right? Why do we have the summation right there, or the integral? Because we're accumulating these terms. How far do these terms go?
Forever.
Infinity, right? You just go forever. All right, so I can write this as a forward difference, right? So here would be the forward difference if I'm now referring to xi plus 1, xi, so xi plus 1, the new value, xi, the previous value, all right? So that's the same as a delta x, all right? So I want to know what's the value at xi plus 1. So here's my Taylor series, right? Okay. If I wanted to do a backwards Taylor series, right? So now I'm going xi minus 1, so that would be the delta x. Notice the sign as it alternates, minus, plus, minus. In fact, first derivative, third derivative, what's going to be the sign on the fifth derivative?
Negative.
Negative, right? Get the idea? Okay, what's a central difference? We have a forward difference, we have a backward difference. We need to know what a central difference is. All right, what you do is you subtract the backward difference from the forward difference. All right? This is forward difference. That's a backward difference. I subtract this from this. What's going to happen when I do this?
All the odds are going to come out.
You notice terms are going to cancel out. Right? What cancels out? This thing. Right? So I'll take that from that. So anything, that'll cancel, that'll add, that'll cancel. All right, get the idea? So here's what I've got. F at xi plus 1 minus f of xi minus 1, all right, is equal to then the first derivative divided by xi plus 1 minus xi minus 1 plus, what's HOT? Yeah, exactly, higher order terms, all right? I can rewrite this first derivative so that it looks like this, all right? Now, remember, if we were going, see right here, xi plus 1 minus xi, that's delta x. xi minus 1, that's delta x. So what would be xi plus 1 minus xi minus 1? Assuming the intervals are the same, 2 delta x. All right, get the idea? There we go. All right, why would we do this? Why would we want to do a central difference instead of forward or a backward?
Is it more accurate?
So I have a question though, shouldn't that be minus the higher order terms?
Here,
Yeah.
it doesn't matter.
Okay.
It doesn't matter on the sign. It just means higher order terms. The signs are inclusive. All right, so what have we done? What have we done here? It's not intuitively obvious until you realize, oh, it's in the subtraction of the terms up here. So remember when we said in the secant method, the first derivative, we use a forward difference, and then you have a higher order term. The higher order term would be that second derivative, right? Now what happens when you take this minus this? What happens to that term and that term? They cancel out, right? So what's left? That term and that term. So this approximation is what we now consider to be second order accurate. In a backward difference or a forward difference, it is first order accurate. So in doing this very simple operation, I've now increased my accuracy by an order of magnitude. Okay? That's the big difference. That's the general technique that is used in solving partial differential equations in many of the commercial codes that you use in transfer, structures, fluids, whatever. They use a central difference approximation. All right, here's what happens. This is the true solution. This is if I do a zero order. This means I'm going to truncate everything. Right? I'll just truncate everything and say, well, the new function is equal to the previous function. So you go, whoops, that's not very accurate. Now if I say, well, I'll keep the first term. So that means it's first order accurate, right? Well, if I keep the second term, right, now it's second order accurate. Why is there a curvature here? Because it's second order, right? Second order allows you to account for curvature, all right? So, would I ultimately get to the true solution? Sure, if I carry enough terms out here. So you see, you're making a judgment call as to say, gee, how many terms am I going to have to carry on this before it's costing me too much computing time or storage or whatever. So I'm just going to truncate these terms. I'll just ignore them. So, but I know that I will have an accuracy associated with that truncation. Okay, so here's a depiction of a forward, backward, and central difference. All right, so here is a forward approximation. This is the true solution, right, the curve. Here would be, say, a backward approximation, depending on what I'm using for the interval, h. H is the same as delta x, right? And then this is what I would get if I'm running a central difference, all right? Notice what I've got here and what I've got here.
That's a big error, isn't it?
Okay, now, this is what's going to happen. When you're actually running these things on various machines, you're going to get a trade-off, and that trade-off is between the round-off and the truncation. So there's a point of, basically, I'm spending too many cycles, and it's costing me too much time, and I'm not gaining anything, all right? So you get what's called the point of diminishing returns, all right? And this is shown here in this slide, where you see the total error. As you start accumulating errors and so forth, it starts doing what? You go, gee, that's starting to increase. I'm not gaining here. Truncation error, all right, round off error. So at what point do you say, this is as far as I want to go? At the minimum, right? So that's what you want to kind of find. And there are a number of tricks that we do, particularly when we're solving complex equations, particularly PDEs, where you say, okay, I need to refine the mesh, or I need to do something here so that I can get as close to the answer as I can, but I don't have to spend a lot of time, you know, running this on the computer, waiting days or weeks for a solution to come back. All right, now, so you want to be careful when you're truncating series and expressions, all right? In the Taylor series, the rule of thumb is that you generally go out to a second order. Second order is the second derivative. If you're going into something like a central difference, if you truncate off at the second order term, what would happen? You wouldn't know what your error would be because, see, you would have truncated off too soon. So here, in this instance, you would have to carry it out to a third term, to the third derivative. There are some numerical methods that you have to carry sometimes these things out to sixth order. And it just depends. If you don't, then you may find out, oh, I don't know what's the true error of the approximation that I'm doing for this particular technique. All right. Also, use absolute error when possible. When would you not want to use absolute error? Do what?
When the number's really, really, really small.
Right. Okay. Now, the reason is if you divide by 0, what happens? The program stops immediately, right? So if you had a phi n plus 1, right? If you're using relative, right? Or absolute, so see what I'm saying? So you have to watch for a division by 0. If your solution truly was 0, and you're saying, oh, if I'm dividing into the difference and it's 0, what's going to happen? Or if it's not quite 0, it's very big, you could get a large error all of a sudden. So you have to kind of balance it. You have to look, have that gut feel where that engineering gap that says, oh, this is what the solution should be. So maybe I need to do a different error calculation. All right, there's an optimal point where truncation versus round off is reached. Okay, anything beyond that, you're wasting cycles, it's diminishing returns. You're going beyond what you need as far as the accuracy of the calculation. All right, if you have a coarse problem, what do I mean by a coarse problem?
Big.
The deltas would be relatively coarse. All right, you can get away with using a coarse approximation, ballpark. Right, so you say this is good enough. How many times have you heard engineers say, well, this is in the ballpark? You know, or this is within 10%. Of course, if you work for the government, it's always within 10%. So sometimes you say, that's good enough. I don't need to get this down to the 10 to the minus 8. Right? I'm just wasting a lot of time and cycles to do that. Okay, when dealing with small numbers, be careful of the precision. Right? If you're running a 32-bit machine and you need to go to higher order, what do? You do what's called double precision. How many of you have ever run across double precision? Okay, so there's a couple of veterans in here. I suggest you talk to them, they know what that means. You can just put a statement in that says, run double precision. Now, if you're running on a 64-bit on the new chips, right, you really don't want to do a double precision. In fact, if you're running on the supercomputer here, which is a 64-bit machine, you really don't want to go double precision, right? Because you're just wasting cycles. Only on the 32-bit machines would you do this. Okay, this is a common technique, double precision, when you're doing things called penalty methods. And that's because you're dealing with very large numbers, usually being divided into very small numbers and so forth. And so you have to get that as accurate as you can. That's in some of the more classic finite element methods. We'll briefly discuss that towards the end of the course. Okay, now, any questions about what we've talked about today? Okay, what we've emphasized, Taylor series. I told you we would come back to that again. The difference between absolute and relative error. Okay. Round off. What do we mean by a forward difference? What do we mean by a backward difference? What is the central difference? I have a tendency to ask you in exams, derive the central difference approximation for the first derivative term, right? Take a look at that in the slides and in your book, and how you do that. Later on, we will discuss how to do that for a second derivative term. Right? Anybody want to guess as to what we do? We want to do a second derivative term? You carry more terms in the approximation in the Taylor series. Okay. Now, any questions on the homework so far?
Just working on the code, that's.
Yeah.
Working on the code. Anybody doing other than MATLAB?
Most has actually started besides us.
And MATLAB actually works.
Okay, yeah. What are you using? You're using MATLAB?
Yeah, who was using that.
Oh, okay, sure.
So that's 4 was started.
One issue I was running into with bisection is the precision.
Yeah.
You're using floating point precision.
Yeah,
When you, if your value is too high,
yeah,
the error, it won't be able to calculate the error accurately, and in that final step, it won't be able to bisect.
yeah.
So I had to calculate the number of iterations it should have taken, and then go that way, rather than do a while statement.
Okay, well, that's one way to get around it, yeah. There's all kinds of different ways to program these things, and it's your logic, whatever you want to use to calculate it. I hope that the example in the lecture notes are of help to you if you haven't looked. And I think in your textbooks, they generally tend to use some example programs. Okay, good. See you on Thursday.
Yeah, I don't know.